So we have a problem, we're given some data, and it's about the time in weeks when babies first crawl. We have a survey of 12 mothers, right? It's known the data is normally distributed. That was one of our requirements, and they ask us to put together an 80% confidence interval for the population standard deviation of the age in which babies first crawl. Okay, so we're estimating a population standard deviation. And we have the data, so we could go find the sample standard deviation on our own, but they actually give it to us right here. S is 10.69 weeks. So again, it's important to know our notation, right? S is the sample standard deviation. So they've actually already given us one of the 3 or 4 things we need to know. Because keep in mind, when we're putting together an interval for a population standard deviation, we're operating according to this guy right here, right? This is a 1 minus alpha. Okay, so C is 80%. That means, right, an alpha is 1 minus C. So this is an 80% confidence interval for sigma squared. This is for the variance, okay, for sigma squared. So you notice we're using the sample variance, which is the square of the sample standard deviation in the interval here. But all we need to know is sample size, sample standard deviation, which we will square for the variance, and then we need to know our 2 different chi-square values, right? We need to find our critical values. So let's go get those critical values. When it comes to critical values, it's really important that we know our symbolic notation. And we started with this reference back in chapter 7. We started to talk about what is z sub alpha. And that, recall, that's the z-score that bounds alpha's worth of area in the right tail. So if I had a normal distribution, right, and that amount of area in the right tail was alpha, then z sub alpha is the z-score, right, on the axis that bounds that much area up there. So when we have some distribution symbol like z or t or chi-squared, and then a sub alpha or a sub anything, it means, right, that reference means it's bounding this much area in the right tail. So when it comes to chi-squared, these are a little more interesting. Z-scores and T-scores, remember, are symmetric. Those are symmetric distributions, but the chi-squared, it is not symmetric. It's a right-skewed distribution. Now, we're working with an 80% confidence interval, right? C was 80%, right? And alpha is 1 minus C. So alpha is equal to 0.20, or 20% here, right? But we don't want to put all 20% in the right tail because we're doing a confidence interval. We want alpha over 2 in each tail. That means 0.10. So we're looking to bound 0.10 of the area in each tail, 0.10. And 0.10 there, right? Well, this guy notation-wise is easy because we call that, right, chi-squared sub 0.10, or that one is chi-squared sub alpha over 2. Now this guy, if you were to actually try to write this notation for it, the one on the left, it's a little trickier because you actually have, right, 0.1 in the left tail. That means you have 1 minus 0.1 or 0.9 over here in the right tail. So notation-wise, this is actually chi-squared sub 0.9 because 0.9 of the area is in the right tail. But if we go to StatCrunch, we can use the calculator and put 0.1 in the left tail, and it just make it nice and intuitive. So let's go to StatCrunch and get these guys. So now I'm in StatCrunch. I just want to pull up calculators, pull up my chi-squared calculator, throw that guy over here in the window so it's easy for everybody to see. And we know the degrees of freedom is n minus 1. The sample size was 12, minus 1 is 11. So we have 11 degrees of freedom. And what we want here is we actually know areas this time, and we want the chi-square values. So it's on less than or equal to, so I'm going to get my left chi-square value first, or this is actually the 1 minus alpha over 2. So I say 0.1. I want 0.1 of the area in the left tail. And that tells me the left critical chi-squared score is 5.578. So now if we go for the right critical value, or chi-squared sub alpha over 2, that is a right-tailed area, and it's 0.1 in the right tail. And that tells me the chi-squared value, right, for the right side, or chi-squared sub alpha over 2, is 17.275. So from StatCrunch, we found that chi-squared sub 1 minus alpha over 2 was 5.578, and chi-squared sub alpha over 2 was 17.275. Okay, now it might seem unintuitive to you. It might seem like this would go on the upper bound and this would go on the lower bound in our interval. But remember, when you divide a number by a bigger number, you get a smaller answer, right? So that actually goes on the left side of our interval. And when you divide a number by a smaller number, you get a bigger answer. And so this actually goes on the right side of our interval. So now it's just plug and play, right? So n was 12 minus 1, right? That's our degrees of freedom right there is what that is, times s squared. Well, if you remember, they gave us s equals 10.69. That was our sample standard deviation, but we square that over chi-squared sub alpha over 2, which was 17.275. We're assuming that's less than or equal to the true population variance, which would be less than or equal to 12 minus 1 times s squared over chi-squared sub 1 minus alpha over 2, which was 5.578. So if we plug and chug on our calculators, you're going to come up with 72.7663 for our left bound is less than or equal to the population variance is less than or equal to 225.3562. Now I rounded to 4 decimal places here as I'm writing for you guys, because remember, if we want the interval to be for the actual population standard deviation, then we need to take the square root of these values. And so I rounded to quite a few decimal places so that when I take the square root, it's still a little more accurate. I actually would just do this with my calculator and wouldn't round off those values at all if I wasn't having to write it down for you in the video. So keep that in mind. You can just do it straight in your calculator. But that should help you out on these intervals. Figured I'd go ahead and throw in the last step just for good measure there. So there would be our interval for the population standard deviation.